Subsurface groundwater. Behavior of water in rocks and soils. Porosity, hydraulic conductivity, and permeability. Instructions for use. The two properties of a rock or soil which are most important in controlling the behavior of subsurface water are A. How much water the rock soil can be hold in empty spaces within it, and B. How easily and rapidly the water can flow through and out of it. The first is defined in hydrogeology by the porosity of the rock or soil. This expresses the ratio of voids in it to its total volume. By definition, the ratio of the volume of void space to that of the solid component is more commonly used. Crystalline igneous and metamorphic rocks have low porosities unless secondary voids such as joints are produced by fracturing in a fault zone or at a fold axis. Porosities of terrigenous sedimentary rocks and soils may also be affected locally by fracturing, but these rocks also have primary voids called pores. Pores are spaces left between the solid grains, and they are distributed fairly evenly throughout the body of the rock or soil when it is formed. Flow of water through a soil or rock is described empirically by Darcy's law, and the relative ease of flow by the hydraulic conductivity, referred to as the coefficient or permeability in some older texts. When water, oil, or gas is flowing through the voids in a rock, its hydraulic conductivity is dependent on its viscosity and on other factors as well as on the properties of rocks. The properties of the rock alone that affect ease of flow are defined by its intrinsic permeability, usually shortened to permeability. Darcy's law. Slow laminar flow of water through a porous medium within which the streamlines are smooth parallel paths, and where there is no turbulence or eddies in the wake of grains, is described by an empirical formula, Darcy's law. The law is valid under most conditions found in nature, where the critical value of the Reynolds number at which turbulent flow develops is seldom approached. The rare exceptions of non-Darcian behavior in the subsurface include flow through leached limestone, especially near springs and in the immediate vicinity of pumped wells. In its simplest expression, Darcy's law is V equals negative Ki, where V, the specific discharge of the volume, water, Q, discharge through a unit area, A, of a porous medium, K is the hydraulic conductivity, I is the hydraulic gradient, that is the rate dH slash dL at which the hydraulic or pressure head of the water, H, measured from a horizontal datum, changes literally with horizontal distance I. Natural circulation of subsurface water, precipitation and its dispersal. The water in soils and rocks below land areas comes from three sources. If we disregard local incursions of brine and some coasts, it may be product or of recent volcanic activity and have separated from magma as juvenile water. Newly involved in the great cycle of natural circulation, this juvenile water is often heavily contaminated with dissolved minerals and gases. Alternatively, it may have been isolated from the cycle of millions of years as connate water, sealed in porous sediment by surrounding impermeable rocks, or lying near stagnant deep within a groundwater basin. If the sediments are marine, the connate water would be saline. Precipitation is dispersed in three ways. A. By evaporation and by transpiration from plants. B. By direct runoff in streams and rivers. C. By infiltration into the ground. Meanwhile, the factors are affecting evaporation are the intensity of the rainfall, the ground temperature, the humidity, and the wind strength. It is difficult to measure it directly with accuracy. Groundwater and the water table. The first ring to infiltrate below the ground surface wets the grain or of soil and adheres to them as pellicular water. The forces holding the water to the grain boundaries are so strong that it is not moved further and can be detached only by evaporation or plant roots. Percolation to greater depths as rain continues to fall proceeds only after the soil reaches its field capacity, at which it cannot hold any more water against the downward pull of gravity. The next water to infiltrate moves over these first fumes of water but does not fill the voids in the rock completely. There is still air present in the centers of the larger void. The pellicular water and gravity water in the unsaturated zone, or zone of aeration, is called Vaduz water. Eventually, the gravity water percolates to a zone of saturation where all the effective voids space in the rock is filled with water. The journey from the surface may take up to a few weeks. The water in the saturated zone is referred to as groundwater, and its upper surface is often referred to, not, not in strict usage of the team, as the water table. Water normally contains impurities such as carbonates and sulfates, which are dissolved from the rocks with which it came in contact. The concentration depends partly on the time in contact, partly on the rate of flow, and partly on how reactive the minerals are. The water from bodies in gravel within a buried channel is usually purer than from other parts, which flow is greater and the gravel is inert compared with clay or limestone. The quality of the groundwater and its suitability for particular purposes, such as drinking or brewing, is thus related to a aquifer containing it. It may also affect the choice of engineering materials for foundation. Groundwater within a high sulfate content is present in some rocks, particularly certain shales and clays. The sulfate may come from gypsum in rock group, from sulfides, from points of hydrogen equal sulfide fluid potential in the equipotential surfaces within the body of groundwater, and this in turn may be used to construct the flow lines of the groundwater. If the soil or rock is uniform and has the same permeability in all directions of flow, then the flow lines are orthogonal, that is, at right angles, to the equipotential surfaces. The pattern of equipotential surfaces and flow lines for a given model of permeability is called flow net. An example is shown in Figure 5.4. In this model of sample topography and uniform permeability perception is everywhere added to the water table, and this source in the system is balanced under steady state conditions by discharge into streams which act as sinks. The diagram illustrates the flow of the groundwater under is symmetric hill flanked by valleys and formed of rocks of uniform permeability. The flow net is correspondingly simple and regular and can be derived analytically. Geological controls on movement of subsurface water. Rocks are grouped into two categories. Those that have relatively high permeabilities because of the pores of the rock are large, or because the rock is well jointed, are referred for brevity as pervous. A body of pervous and permeable rocks capable of yielding groundwater is called an aquifer. Rocks with low permeability and no fissures are referred in the following account as impervious. They are aquicludes. If gravity water percolating through the unsaturated zone meets a layer or length of impervious rocks, for example, a length of clay and gravel, then further flow downwards is hindered and local zone of saturation is formed above the main water table. It is called a perched water table. This drains slowly by flow over the edge of the lens.
Hi, my name is Colleen Gonzalez, and for today, I will be discussing and reporting about the natural discharge of groundwater. Natural discharge of groundwater takes place where the ground surface intersects the water table. If the flow from the hydrologic unit is spread diffusely over an area of marshy ground, it is usually referred to as a seepage. If it is concentrated, say by a fissure acting as a channel, it is called a spring. A valley spring occurs where the water table intersects the bottom of a valley that is cut into pervious rocks. If the water table rises and falls seasonally, flow is intermittent, then the spring is called a bourne. So in here, we have mentioned the seepage. So what exactly is a seepage? So when liquid or gas slowly leaks through tiny holes or gaps in a container or barrier, it's called a seepage. The seepage of rainwater through the foundation of your house can result in a very damp basement. Seepage is the process of something seeping or leaking extremely slowly. Now, let us move forward to the definition of spring. I know that we all are familiar with the word spring because it has been mentioned a lot of times in water-related commercials. So what exactly is a spring? The discharge of a spring, also called its flow, is the volume of water passing a certain point during a certain time. Measuring spring flow is another way of characterizing a spring's overall condition. It is typically measured in cubic feet per second or in million gallons per day, although smaller springs can be measured in gallons per minute. Discharge measurements from a spring also have a directional component, and later on, the spring water can be called bourne when the flow of water is intermittent. So in the next slide, we have here, if the intersection of surface and water table is controlled by geological structure, and discharge takes place where impervious rock bounds the hydrologic unit, the overflow is called a contact spring, or sometimes a stratum spring if the rock is layered. The impervious barrier may be a layer of clay or shale, or an igneous intrusion. By converse argument, a spring line known to be related to a particular geological contact may be used to trace its outcrop laterally when mapping. Fault springs occur where pervious rocks are faulted against impervious rocks and may be thought of as a type of contact spring. So if the rock in the fault zone is pervious breccia, a natural artesian flow may bring confined water to the surface from a concealed aquifer. In desert areas, this flow may produce an oasis. So, contact springs are formed where relatively permeable rocks overlie rocks of low permeability. A lithological contact is usually marked by a line of springs. Such springs are usually associated with perched aquifers in mountains. Stratum springs, on the other hand, is formed where the downward flow of groundwater is prevented by an underlying impermeable layer of rocks, which can result in a line of springs emerging at the boundary between the two layers. So now that we have given the definition of the contact spring and stratum spring, we should also discuss what spring line is. So a spring line is the intersection of the natural water level in the ground with the surface along which springs are commonly found. Also, fault springs are formed when faulting gives rise to the conditions favorable for spring formation as groundwater under hydrostatic pressure can move up along such faults. Okay, moving on. In limestone areas, groundwater usually follows channels along bedding planes or fissures, which are progressively widened by solution, and discharge from limestone is often from solution channel springs. Solution channel springs typically occur in limestone districts where groundwater has created caves and channels by dissolving calcium carbonate along bedding planes and fractures, and then return to the surface where impermeable strata prevent further downwards migration. So I researched about the limestone areas, and these are the location where most of them are found in shallow parts of the ocean between 30 degrees north latitude and 30 degrees south latitude. Limestones is forming in the Indian Ocean, Gulf of Mexico, around Pacific Ocean islands, and within the Indonesian archipelago. Solution channel springs, meanwhile, is an elongate void within a rock, which has been enlarged by the solution action of moving groundwater on the rock itself. Solution channels are most commonly associated with carbon rocks, and groundwater in them can flow as fast as in a river on the ground surface.
Some practical engineering aspects of groundwater. Groundwater and engineering. The presence of water in rocks and its movement through them are of great importance to many human activities such as farming. However, this brief account is limited to some of the more important geological aspects of groundwater which are linked to engineering. These are A. Water supply from subsurface sources. B. Drainage of marshes. And C. Disposal of toxic waste underground. Groundwater inventory. In assessing the feasibility of any scheme of groundwater supply and in planning it, geological and hydrological information is essential. A first step is to evaluate the permeabilities of the rock and soils present in the area and to determine their structure. This identifies aquifers and aquicludes and outlines the hydrologic units present. The common aquifers include A. Sand and gravel deposits occurring in the drift and glaciated areas, or as alluvial cones, especially in semi-arid hilly regions. B. Sandstones, for example, the Bunter sandstone and Kuiper sandstones, waterstones, in the English Midlands. C. Certain permeable limestones, such as chalk and fissured or deeply weathered igneous rocks, especially in tropical areas. Potential supply of groundwater from the hydrologic unit selected for investigation is then assessed by drawing up a groundwater inventory by evaluating the equation. Total perception is equal to evaporation plus direct runoff plus groundwater. The safe yield of the hydrologic unit is equal to its groundwater increment. If more water than this is withdrawn by pumping from deep wells, then finite reserves rather than current resources are being exploited. This may be justified during a summer drought, but as standard practice over years, it will produce a serious drop in level of the water table or the piezometric surface of the aquifer. The, this can be monitored using wells in coastal areas. Careless exploitation may lead to serious settlement and to invasion of irrigation wells by brine. Seeding and testing of individual wells. Wells may be dug or bored either to get fluids out of the ground or to put them into it. Those for water supply are best bored in such a way that the sides are supported with the use of a mud flush, which might clog the aquifer, and they should penetrate its full thickness. They vary from a few meters in depth to 600 meters in some cases. An average yield is about 40 liters per minute, but may be as high as 4,000 liters per minute. To complete the well after boring it, a gravel filter is placed near the bottom, and is held in place by a slot inner lining tube. Weak acid is pumped down oil wells producing from limestones to improve flow around the well by opening fractures. The acidation treatment can add up about 15% to the total costs of a water well in chalk or other limestones, and has not been common practice, though it is other worthwhile by some experienced engineer. For this reason, the prime geological factor in choosing the precise site for a boring is the probability that the permeability of the aquifer is higher at the locality or that flow is assisted by fracturing. In water table wells is pumped from an unconfined aquifer where, in confined water wells, the whole aquifer penetrated by the well is saturated and there is usually artisan's pressure. Once withdrawal of water from a well is underway by pumping or artisan's flow, an inverted cone of depression of the water table forms around a water table well. Its slope is related directly to the level below the water table at which pumping is taking place and inversely to the permeability of the rock surrounding the well. Wells 1 and 2 are sited so close to each other that their cones of depression interfere with one another to produce a lowering of water table between the two wells. This reduces the hydraulic gradient in that sector around the well and lowers the flow into them and their yields. The same phenomenon can, however, be put to use in draining those soils prior to excavation, as the ground between the two wells can be dewatered in the same way. Drainage of groundwater. The removal of groundwater from soil is the main aim in reclamation of marshes, and it may also be important in other projects where, for example, the stability of a slope is affected by saturation. This excess water may be replenished by infiltration or by subsurface flow into the saturated zone of which it is part. If martially ground is an area of seepage, then the system of drainage should be devised not only to drain the excess water stored in the soil but also to cut off the source of supply by lowering the water table. Dewatering can be a slow process in clayey soils, and drainage may be speeded by electroosmosis. If two electrodes are placed in saturated soil that has a colloidal contact, then water molecules tend to be carried by movement of positive ions toward the negative terminal cathode. The flow is greater than would otherwise be achieved by normal gradient of water table, as the electroosmotic permeability is much higher than K. Using a perforated tube for the cathode, water can be pumped from it. Disposal of toxic waste and storage of fluids underground. Underground disposal is an acceptable practice where local geology and hydrology are favorable and where are those reduce engineering and administrative controls. The most important aspect geologically is that there must be a negligible rate of groundwater movement near the storage area. For example, salinity of the groundwater at the storage area would indicate this it is connate and would be useful criterion of limited flow through the rock. Disposal wells for toxic waste basically require a previous reservoir layer of sandstone for injection, overlain by an impervious layer of shale or salt which seals it. Groundwater flow should be very slow since any movement carry a risk of contaminating neighboring water wells or springs. Oil traps can be used to store imported natural gas, and a few schemes of this type exist. Theoretically, they could be used to store strategic oil reserves, but only at an acceptable cost. With present technology of not being able to recover a large percentage of the oil in the reservoir. So far, underground storage of oil and of liquefied frozen gas has been in large artificial caverns for oil. These are excavated in impervious rocks. For liquefied gas, they are excavated in soils or soft rocks. And the groundwater frozen by refrigeration makes the walls of the cavern impermeable. Accumulations of petroleums, that is, of oil and natural gas, occurs naturally in structures of this type, which are called oil traps. The disposal of radioactive waste is an increasingly important problem that demands careful study because of its scale and because of consequence of any misjudgment. The conventional solutions, depending on the level of radioactivity, have been succinctly as A dilute and disperse, B delayed and decay, and C concentrate and contain. Small quantities of highly radioactive waste can only be disposed of safely in the last way. Methods used or proposed for long-term storage including the following: A. Excavating a storage chamber in a layer of bed salt and a depth of 300 meters in Kansas. The salt is dry and impervious, and its flow under pressure would close any fracture that develops. It is a good heat simulator and has enough strength to support shafts and room during mining. B. Placing the liquid waste in a cement mix and injecting it under high fluid pressure into the deep shale layers. The high pressure produces local fracturing and makes possible the injection into shale.